In the previous lecture 4, part 1, we have studied one particular algorithm, namely ID3, which is to build a decision tree from a given training database. In that lecture, the classification problem we considered is called the binary classification problem because we have two classes, namely the positive class and the negative class. And then each training data object either belongs to the positive class or belongs to the negative class. What if in practice you have multiple classes, or you have n classes where n is greater than 2? For example, you might have 3 classes, class 1, class 2, class 3, and the data objects belong to these 3 classes. How you are going to do the classification? In this case, what we do is we can either modify the formulas for calculating the entropy and the information gain used in ID3 algorithm. And a lot of papers have talked about how to modify the formulas so that the formulas can work for 3 or 4 or 5 classes. So that's one strategy. Another strategy we could use is to consider each class in turn. For example, you consider class 1, and then you group all the other classes into the so-called non-class 1. So now you have class 1 and a non-class 1. Now once again, this becomes binary classification because you have class 1 and a non-class 1. Non-class 1 contains all the data objects that are not in class 1. So those objects belonging to class 2, class 3, class 5, and so on, right now all go to the non-class 1. All right? So you look at the given training database in which you have a lot of data objects and you have labels for these data objects. That is, for each data object, you know which class that object belongs to. You have a label there. Okay, it could be class 1, could be class 2, could be class 3, and so on. And then you divide these data objects into 2 classes. For an object which belongs to class 1, you put that object in class 1. For an object that belongs to class 2 or class 3 and so on, you put that object in non-class 1. So once again, in your training database, you are able to just put the objects either in class 1 or non-class 1, and then this becomes a binary classification problem. Right now you have a binary classification problem, so once again you can apply the ID3 algorithm to build a decision tree using this training database, using the previous formulas we have learned in the previous lecture. Okay, so that basically is to look at class 1 first. And then you also look at class 2 and the non-class 2. What does non-class 2 mean here? Non-class 2 contains those data objects that do not belong to class 2. That is, they could belong to class 1 or class 3, class 4, and so on. So once again, for the whole training database, you can put the data objects either in class 2 or in non-class 2, where the non-class 2 contains all the data objects that don't belong to class 2. And again, this is a binary classification problem, meaning that your data objects either belong to class 2 or they don't belong to class 2. So you have a positive class and you have a negative class. All right? Now, once again, you can apply the ID3 algorithm to build a decision tree based on your training database. Right now, this decision tree could be different from the previous decision tree because right now, your positive class is class 2 as opposed to class 1, and your negative class is non-class 2. as opposed to non-class 1. You can do so by looking at each class in turn. So suppose you have 10 classes. Then by applying the ID3 algorithm, you will end up with 10 different decision trees. And from each decision tree, you are able to extract classification rules from that decision tree. So you will get a lot of classification rules from these decision trees. And then you can use these classification rules to classify a newly given unlabeled data object. By saying an object which is unlabeled, we mean that we don't know which class that object should belong to. So we want to use the classification rules to classify that object, to assign that object to an existing class. Okay? So that's basically the idea for generalization to multiple classes for classification. And interesting enough, when you apply this algorithm and when you end up with these entries and the classification rules extracted from these entries, there's no conflict between these rules, meaning that they should be consistent. You won't see conflicting rules among them. All right? ID3 or C4.5 is one of the most famous classification algorithms. And that algorithm, as we pointed out last time, is suitable for categorical attributes with non-continuous values. There are many other classification algorithms that can be used for continuous values, okay, or for some other type of attributes. Here, I'm showing you two additional class files. The first one is called the k nearest neighbor class file. When k is 1, this class file is known as the nearest neighbor class file. What does this class file do for us? Suppose you have 10 classes. Okay? So you put those 10 classes there. Suppose you have a new data object that is submitted to this system, and you want to assign this object to one of the 10 classes. Now, in this class file, we require that we have a distance function so that we can use that function to measure the distance between any pair of objects. So for the new object, what we do is we calculate the distance between that new object with every object in the system. So suppose you have 100 objects grouped into 10 classes. Then for the new object, you calculate the distance from that new object to the 100 data objects. So you get 100 distant values, right? Then you can sort the distant values, and you are able to identify which data object has the smallest distance from the newly given unlabeled data object. So you can find the smallest distance. Suppose the object that has the smallest distance from the unlabeled data object belongs to class 5. That is, the nearest neighbor of the unlabeled data object belongs to class 5. For that case, we assign this unlabeled data object to class 5. So the algorithm is to assign the unlabeled data object to the class where the nearest neighbor of this unlabeled data object belongs. So that's the whole idea of this nearest neighbor class file or nearest neighbor classification algorithm. Okay? So for any given new object, you look at all the objects in the system. If that object is closest to me, so I should belong to that class where that object belongs. That's the whole idea of this algorithm, which is simple, which makes sense because we look more similar, so we should be in the same class. Any question on this algorithm? Louder, please, Tony.
It's not very clear to me what the distance depends on. How do you calculate the distance?
That's a very good question. The question raised by Tony is that what do we mean by a distance function? So to answer your question, I just give you a very simple example. Look at all the students in this classroom. I stand here. Who is nearest to me in terms of geometrical distance? Who is nearest to me? Right, he is nearest to me. So that's one distance function. So here the distance function is calculated in terms of a geographical distance. He is closest to me, so he is nearest. Now, so your question is, how do we calculate distance functions in general? That's a very big question. And in fact, most of my research has been focused on calculating distances between data objects. For those of you who come from mathematical who come here with a mathematical background, I think you all know the Euclidean distance in the Euclidean space, right? Three-dimensional Euclidean space. And there you also have a distance. So distance, the notion of distance exists everywhere. All right? And how to calculate them is another issue. There are thousands of algorithms that have been published to calculate distances between data objects. For different data objects, we invent different distance functions. I give you two examples already. Geometrical distance or geographical distance and the Euclidean distance. But there are many other distances. You check my website, click on the publication page. You go there, you can find a lot of papers talking about calculating the distances between trees or graphs. So for trees, you can also find distance between them. And the problem is non-trivial, by the way. For graphs, the problem is NP-complete, even for the 80 distance. So the problem is very difficult. And a lot of algorithms have been published to solve this type of problems. For strings, there are a bunch of algorithms that run in polynomial time for calculating the distance between strings. Why strings are important? Because all the protein sequences, DNA sequences, and so on are modeled as strings of characters. And therefore, these distance measures are important for calculating their distances. And therefore, a lot of research has been done in that area. Why we care distances? Well, if you look at the practical world, suppose you have two protein sequences. Wouldn't it be good if we know how similar they look to each other? When you use a similarity, that's a distance idea. Okay? So the notion of distance is an important one. It's also a non-easy one. So we will look at more distances as we go to the next lecture, clustering. Okay? The clustering algorithms depend more on distances. The next classifier is called the k nearest neighbor classifier, where k is greater than 1. Suppose, for example, we consider 3 nearest neighbor classifier. How this classifier works? The algorithm works as follows. Suppose you have a new unlabeled object, meaning that you don't know the label of the object and you don't know which class that object should belong to. What you do is you look at 3 nearest neighbors of this object. This object is nearest to this newly given object, and that object belongs to class 3. This object is second nearest to this new object, and that object belongs to class 9. Another object, which is the third nearest to the given unknown object, and that object again comes to class 3. For that case, we take the majority vote. 2 objects that are closest to me come from class 3, so I should belong to class 3 as well. So we take the majority vote. Okay, that's how the 3 nearest neighbor classifier works. You look at the 3 nearest neighbors, and then suppose the majority of these nearest neighbors come from class K, then this object should belong to class K. Neural networks. Neural networks is another very important classification tool or unsupervised learning tool. Okay, this is a supervised learning tool in the sense that a neural network should be trained first before it performs classifications. Once again, this is a big area, and I encourage you to look at my website, go to the publication webpage, and there you can see several papers about applying neural networks to classifying DNA and protein sequences. A neural network usually contains 3 layers: input layer, hidden layer, and output layer. And there are a lot of neurons in these layers. And then for a given object, the object is fed into the input layer. And then through the, some mathematical functions and the calculations, the output layer will tell us whether this object belongs to the positive class or it should belong to the negative class. One very interesting classification problem in applying neural networks to classification is that we usually would like to do feature extraction from objects when we do neural network classification. That is, neural networks usually cannot handle objects or the raw objects on its own. What we have to do is to extract features from these objects and then feed the features to the neural networks, where features are usually represented as vectors. Vectors are points, for example. Okay? Many objects are not having numerical values. For example, a DNA sequence is a character string. It's not a numerical value. So it's very difficult to feed this character string to neural networks where basically we use mathematical formulas to calculate vectors and so on. So what we do is to translate this character string into a vector first, and then feed the vectors to the neural network. And that transformation is non-trivial, by the way. Okay? Translating a character string to a vector is non-trivial, and this process is often known as feature extraction. And there are numerous algorithms published in feature extraction trying to transform raw data objects to vectors suitable for neural network classifications. And if you look at my webpage, publication webpage, you will see one paper published in 2001, invited in the IBM System Journals. And that paper is dedicated to extracting features from protein sequences and then classify the protein sequences based on neural networks. Okay? So you can find this sample works or sample papers on my website. And from the papers, you can find more pointers to relevant references or to this field. Okay? And this is a big area. I always encourage you to look at additional references or additional resources as we go through these lectures. Okay, now we have a classifier. Suppose we use the ID3 algorithm and we build a classifier right now. How do we know how accurate that classifier is? How do we know whether that classifier is good or bad? How do we know whether the classification algorithm is good or bad? We need to have some measures to evaluate the accuracy of a classifier. And we need to know how to conduct experiments to calculate these accuracy measures. Okay? And there are several strategies to evaluate the accuracy of classification. I give you two strategies here, but there are numerous other strategies, okay? In fact, the second strategy, cross-validation, is a strategy we use most frequently in our research to evaluate the accuracy of a classifier. Okay, so the whole idea is that right now you devise or you invent a new classification algorithm. But how do you convince people that your algorithm can be used tomorrow to actually classify unknown, unlabeled object? How do people trust your classifier? You have to present some experimental results that show people that, look, my algorithm is working well for experimental data, so that people can be convinced and people can actually use your algorithm or your program to do classification tomorrow for unknown, unlabeled objects. When you try to convince people that your work can be done, can work well in the future, the best thing to do for you to convince people is that you show them that you can actually do well for existing data. You can actually do well for the history, for the past, before you want to convince people that you can do well for the future. Am I right? Nobody knows what future will be. So nobody can actually predict the future. So what we do is we say, look, my algorithm or my classifier can classify the historical data or the existing data very well. And therefore, my classifier should presumably do well tomorrow. Right? No one knows what will happen tomorrow. But we can trust you if you demonstrate that your algorithm can do well on existing data. So the binary partition strategy is the following. Suppose right now you invent a new classification algorithm, which could be ID3, C4.5, k-nearest neighbor, or a neural network. You know, people publish algorithms every day. So you publish a new classification algorithm. So the next thing to do is you show people that your algorithm works well and works correctly. And then to do that, you take a big database in which every data object has a known label. That is, their class is known. So this object belongs to class 1, that object belongs to class 2, this object belongs to class 3, and so on. The data is known. All the labels of the objects are known and are given. You say, look at this training database. I use a binary partition strategy in such a way that I divide this database into two sets, the training data set and the test data set. Normally, 2/3 of the data objects belong to the training data set, and 1/3 of the database belongs to the test data set. I have to remind you that even though we call it a test data set, all the data objects in that test data set still have known labels. That is, their classes are known in advance. Everything is known. All right? You know this object belongs to class 5. You know this object belongs to class 10. Their class information or their labels are known already. Okay? Okay, then I try to simulate the whole classification process one time in the following way. I use the 2/3 training data set to train this classifier. For example, you use the 2/3 training data set to train your ID3 algorithm to build a decision tree. Or you use the 2/3 training data set to train your k-nearest neighbor classifier, okay, to get a classification tool. So now it is trained. And then you test this classifier, your classifier, using the remaining 1/3 test data objects. Use these data objects to train your classification algorithm or your classifier. Okay? You send this test object to the classifier pretending that you don't know its label. And then the classifier will tell you, okay, for this test data object, it should belong to class 9. And then you look at its label. You know its label, right? As I said, all these data objects have existing labels, have their classes known in advance. The classifier says this object should belong to class 9. You check the class information. Indeed, this object belongs to class 9. And then you say that, okay, the classifier is correct for this data object. Then you look at the next test data object. You send this test data object to the classifier. And the classifier says, after this calculation, this data object should belong to class 6. And then you look at the label. you look at the label, you look at the class information. Yes, indeed, it is in class 6. So now again, this classifier is correct for this test data object. Then you send the third text object, the next text data object, to the classifier. The classifier says, okay, based on calculation, this data object should belong to class 5. But now this time you look at you check the label of this data object, it belongs to class 1. So now the classifier makes one mistake, right? Suppose totally you have 300 data objects. 2/3 of them are used for training. So 200 objects are used for training. Now you get a classifier. And 100 of data objects are used for testing. Out of these 100 test data objects, the classifier makes 10 mistakes, meaning that the classifier says this test object should belong to class X, while in practice, in reality, this data object belongs to class Y. So that's a mistake made by the classifier. And you count how many mistakes this classifier has made. Suppose out of 100 test data objects, the classifier makes 10 mistakes. Then we say that this classifier has an accuracy 90%. Meaning that out of 100 test data objects, it is correct for 90 data objects, but it makes mistakes for 10 test data objects. So the accuracy or the accuracy or actually we use the major accuracy. The accuracy of this classifier is 90%. All the error rates for this classifier is 10%. So that's how we can tell people after we do the experiments. Any question about this binary partition strategy? Yes, louder please.
I want to know that the training set, the number of objects in the training set can dominate the accuracy. I mean, even for very good classification algorithm, if the training set is very small, the accuracy will be low.
Very true. Very true. So your claim is that if we have too few training data, the result will be unsatisfactory or will be biased, which is very true. So what we do is normally we use 2/3, 1/3, but sometimes 2/3, 1/3 is still not good. So we use 9/10 versus 1/10. 9/10 of the data are used for training, and 1/10 of the data are used for testing. And that leads to the next strategy, which is called a cross-validation strategy. In this strategy, we divide the data set into k partitions and use k-1 partitions as training data and 1 partition as test data. And we rotate this k, okay, in such a way that in the first time, this partition is used as training data and the other k-1 partitions are this partition is used as a test data, and the other k-1 partitions are used for training data. And then in the next run, we rotate this. We go to the next partition, and we use that partition as a test data, and the other k-1 partitions are used for training data. We keep on rotating this k, and normally, when k is 10, we get the best result. So this ends up with the so-called tenfold cross-validation. What does tenfold cross-validation do for us? We divide all the data objects whose labels are known in advance into 10 partitions. In the first run, we choose partition 1 as the test data set, and the other 9 partitions as the training data set. And then we use that in that run, we use the training data set to train the classifier, and then use the test data set to test the classifier. We can get an accuracy. Suppose the accuracy is 90%. I just give you an example. You memorize this accuracy. And then in the second run, you rotate this partition. Now in the second run, you use partition 2 as a training data set, as a test data set, and you use the other 9 remaining partitions as a training data set. In the third run, you use partition 3 as a test data set, and use the other 9 remaining partitions as a training data set. You keep on rotation. It's just like you have a window, right? In the first run, your window is pointing to partition 1, and that partition 1 is used as a test data set. The other 9 partitions are used for training data set. And you do the classification, you calculate the accuracy. In the second run, you rotate the window slightly, you shift the window to the right a little bit, so that now the window points to partition 2. And in the second run, partition 2 is used as a test data set. The other 9 partitions are used for training data set. Now, once again, in this environment, you can do the calculation of accuracy. In the third run, you rotate the window again slightly by shifting to the right a little bit, so that right now partition 3 is facing the window. So partition 3 in this run is used as a test data set. And the other 9 partitions, partition 1, 2, 4, 5, 6, and so on, the other 9 remaining partitions are used for training data set. So you keep on rotating these windows. And so you can end up with 10 different rounds. In each round, you can calculate an accuracy. At the end, you add up all these accuracy numbers and then divide the sum by 10. You get an average. And that average gives you the accuracy of this class file. And this experimental setup is known as tenfold cross-validation. And this is the most commonly used strategy for us to evaluate the accuracy of a class file. Is that clear to all of you? So you do 10 times of experiments. In each experiment, use a different partition as a test data set and use the other 9 partitions as a training data set. And you can calculate the accuracy in that environment. And then in the next one, you change the partition, you change the test data set, and so on. And that's known as tenfold cross-validation. In fact, if you look at my papers, almost all the papers are based on the tenfold cross-validation to evaluate the accuracy of our class files. We developed a lot of class files in the past, and every time we just use this tenfold cross-validation to set up our experiments and to evaluate the accuracy of our class files, and then we publish the results obtained from this tenfold cross-validation. Tony, louder please.
Do you take an average of the different accuracies calculated, or you have to have a threshold in order for an algorithm or classifier to be considered?
I have 10 different runs, right? So I get 10 different numbers for accuracy, right? I sum up this, I add up these 10 numbers divided by 10, I get an average. That's usually how we do for the tenfold cross-validation.
Is there any threshold accuracy that is considered?
That depends on the environment. For example, right now, in classifying proteins, most people can accomplish 95% or 96%. If you are below, your classifier is considered as a poor classifier. Okay, that depends on protein sequences, of course. But in most published protein sequences, like those in the Swiss Pro or those in the PR protein database, we can accomplish it at the level of 90% or 92%, okay, which is pretty high. On the other hand, for DNA sequence classifications, in particular, when we try to predict promoter sites in DNA sequences, in eukaryotic DNA sequences, depends on the data. Sometimes perhaps you end up with a classification rate like 60% or 50-something. And so for that case, because the data is so difficult to distinguish, so no matter how good your algorithm is, you just cannot distinguish the data clearly. I remember that we published our algorithm for protein sequences, and our algorithm can accomplish 96%, and we present this in the NIH, and one NIH person says, okay, look, your classifier is good, so could you please classify these sequences I just obtained from my experiments? And he gave us sequences. And we look at the data. The data is not distinguishable at all. Even human beings cannot see the differences. So our classifier ends up with like a 50%, meaning that it's a guess. 50% is guess, right? You throw the coin, right? You say this is either the head face up or face down, right? It's a guess. You throw the coin. So 50% classifier is very poor, okay? When the data is very difficult, your classifier cannot do better. So classification depends on data very much. You have to keep this in mind, all right? In usual cases where your data are distinguishable, then you can try to develop classification algorithms as much as you can so that your algorithms can work well on this data. On the other hand, if data is non-distinguishable, no matter how good your algorithm is, your algorithm cannot do better. Okay, you look at this bottle, right? You look at another bottle. They both look the same. They have the same shape. They contain the same thing, water. For that case, it's very distinguishable whether this comes from Portland Spring or that comes from another company and so on, because they all look so similar. You see my point or not? So classification depends on the domain. When the domain becomes difficult, the classification can be an extremely difficult task. No matter how, how good algorithm we develop, it just cannot work. Okay, so that's the accuracy of classification. There are many research issues in this field, and that's why classification is still a very active area in data mining. If you go to data mining conferences this year or next year, you will still see a lot of papers publishing the classification in different domains. One research issue is data cleaning. In reality, data could be dirty, meaning that you have a lot of errors in the data. A lot of DNA sequences extracted from human beings are not very correct yet. So they post these sequences on the website, and after 2 days, they modify the sequences. So you keep on seeing different sequences. Because the data is not clean yet. They are still doing the job, and therefore the data are very preliminary. Data could be very incomplete. You look at the real world. You look at the tuples, look at the relational databases. A lot of tuples have incomplete values for certain attributes and so on. So attribute values are missing. Okay, so data is incomplete. Data might be dirty. There might be errors in the data. So if you are given very incomplete data or error data, how can you expect your classification algorithm works well on that data? Data is not clean. If you use that data to train the classifier will not work well, right? If data is wrong, the wrong data gives the classifier wrong information, and therefore the classifier will not be able to work correctly. Okay, so data cleaning is very important in order to get a correct classifier. Data reduction, another very important research issue. In reality, if you look at the databases in Walmart or in other big supermarkets, you have thousands of tuples in the transaction database. And for each transaction, you might have a lot of attributes. Many of these attributes are irrelevant to classification, or many of these attribute values can be combined together. For that case, we would like to reduce, for example, a tuple with 100 attributes to a tuple with only 5 attributes, and then work on those reduced tuples. Use those reduced tuples to train the classifier. So that is called the relevance analysis. You try to do the relevance analysis and pick up only relevant attributes and their values, and use those reduced tuples to train your classifier. Feature selection. In neural networks, when we use neural networks to classify data objects, the raw data objects are not suitable for neural networks. For example, protein sequence is a character string, while neural networks usually deal with vectors of real numbers. For that case, we have to extract features from protein sequences or DNA sequences and transform them to vectors and feed these vectors to neural networks. Okay? And this transformation process is known as feature selection or feature extraction. You have to extract features from raw data objects and use features to do classification. Dimensionality reduction. In data warehouses, a lot of tuples have high dimensions, a lot of dimensions. Okay, so in many cases, we would like to reduce the dimensions. Accuracy of classification. Okay, after you build up a classifier, you would like to develop strategies to evaluate the accuracy of your classifier. You could use the binary partitioning strategy, but most often you use a tenfold cross-validation strategy to evaluate the accuracy. Sometimes to avoid biased conclusion, you want to do more other type of experiments to evaluate the accuracy of your classifier. Speed. You want a classifier to do the work in a fast way. In the training phase, it takes a lot of time. Like in our classifier, in our DNA classification paper, we train the classifier using 2 or 3 days. But once it is trained, it should classify things quickly, in less than 1 second, for example. So you spend a lot of time in training, but during the testing, in the online phase, the classifier should work very fast. Okay, when an object is given, the classifier should tell you immediately that this belongs to class X. Okay, we want the speed. Scalability. Many classifiers work very well in small data sets, but when the data sets become large, the classifier just collapse. So how to develop scalable classifiers? That is, a classifier that can work well in large data sets is also an important research topic. The classifier should be usable, and the quality of the classifier should be high. The classifier should be robust in the sense that even though in reality you have unclean data, your data have noises, your classifier should be able to handle noises and incomplete data and give you unbiased prediction. So all these are research issues, and a lot of papers are being published to address these issues for different types of data in different domains. And that basically concludes this lecture, classification. For those of you who are interested in this field, please feel free to go to my website and you can download papers there. I've done a lot of work in classification in the past 10 years. We do classification in various domains, mostly in biology, but we also deal with classifications in other domains. So you can look at them and you can find the different classification algorithms, modifications of neural networks, and also these nearest neighbor classification algorithms and so on. We have tried many of them and published many of them, the new algorithms for classification. So here's the homework 2. I'm going to post the due date for homework 2 in the web board. Okay. Here is the details of the homework 2. Homework 2 is to ask you to build a decision tree given the training data set on the following transparency. I want you to generate a decision tree and extract all rules from the decision tree. Okay? By the way, in the exam, the questions will be very similar to what you see in the homework. So this is a good chance for you, good opportunity for you to exercise it. Okay? So this is a given training data set, and you are asked to build a decision tree based on this training data set using the ID3 algorithm we have discussed in the previous lecture for part 1. In this training data set, look at for example, the first tuple. The income of that person is median. Marital status is single. That person lives in New Jersey. That person is driving a sports car. For that case, yes, that person subscribes car magazine. So yes means that person subscribes car magazine. No means that person does not subscribe car magazines. So now again, this is a binary classification problem where your labels are either yes or no, positive class and a negative class. So use this training data set to build a decision tree, and then you extract these classification rules from that decision tree. So that's your homework 2. And that basically concludes our lectures for classification.